Good day. Today is a great day for mathematics as usual, and we got another video for you. The discriminant of a quadratic. Hold the phone, Beck. What's up? We already did that. Well, this, boys and girls, is part 2 because we didn't quite finish last time, and I wanted to cut it and not go on and on and on and on. Blah. So today we're going to focus on bullet 2 and bullet 4. Want to talk about those and a little bit more extensively and what in the world this exactly means, just to make sure you get it. Two distinct real roots if delta is greater than 0. First of all, remember our real number system is made up of the rational numbers and the irrational numbers. And rational numbers can be written in the form of A over B, A and B elements of the integers, and of course B not equal to 0. And what that boils down to is you can write any rational number you can write as a fraction using integers. Irrationals you can't. What are examples of irrationals? Like square root of 2, pi, the number e, any square root that is not a perfect square is an irrational number. That's what really comes into play here. So we get two distinct real roots, and we're going to contrast that to down here where we have two rational roots. And distinct is really important. Distinct means different. Okay. Quick example. If I had let's see. Let's try this. X squared minus x minus 3 equal to 0. And I took a look at the discriminant. That would be positive 1 minus 4. If I ever have a positive 1 in the 4AC, I just forget about it. Like in this case, a is positive 1. So that's 4 times 1 times negative 3. So that would be 1... Oops, times negative 3, sorry. Okay, so that would be 1 plus 12 or 13, so delta equals 13. Which means in the quadratic formula, or the quadratic equation, I would have root 13, remember, and plus or minus in front of that, and blah over blah. And I would get two solutions that just wouldn't turn out too nice. I can't factor this, so I just get two real solutions, and they're real numbers. Square root of 13, if I add or subtract it, I can't write it as a fraction, so I'm going to get real solutions. So that's what that means, and we'll take a look at the graph in just a second. Down here, if A, B, C are rational and delta is a square, what do they mean by that? Well, they mean perfect square, you know, like 1 or 25 or 9, etc. Your perfect squares. Then the equation has two rational roots, which can be found by factorization. And all that means is we have roots that can be written as a fraction, that can be written as a rational number. We still have two real roots, but here we're saying two rational roots, and they may or may not be distinct, and we'll talk a bit more about that in the next example on the next page. But let's just talk about having delta as a perfect square. For example, if we had, let's see, 2x squared minus x minus 1 equals 0, and I found delta. Well, delta would equal b squared, so negative 1 squared is 1, minus 4 times a times c. In this case, it's negative 1, so I am going to write it because the negative makes it important. That makes us 1 plus 8, which equals 9. So delta is a perfect square. That means it's factorable. And I'm going to be able to have, if it's factorable, that means I'm going to have rational solutions and or rational roots, and I'm going to have two of them. Might have a double root. That occurs when there is a perfect square trinomial. More of that in a sec. Okay, so this factors easily 2x x, we're going to have 1, 1, and the only question is what's plus and what's minus, and it turns out that this is plus, this is minus, and so just looking real quick, we get x equal to negative 1/2 or x equal to 1. Okay, so again, we had a perfect square for delta, which means that the quadratic is factorable, and we have two rational solutions, which means we can write the solutions as fractions. Whereas here we had two distinct real roots, but we couldn't write them as fractions, as rational. So that's why we just called them real roots. These are distinct too, but we can't put a blanket around them because sometimes they're not distinct, sometimes they're not different. The solutions, you would have a double root and one solution if that was the case. So let's take a quick look at the graph, some graphs here. Now this is, let's look at this one, the F9 here. It's the first example I did, x squared minus x minus 3. And if you look where the green graph intersects the x-axis there and there, you can kind of tell that those are not nice rational numbers. You know, you might say, Mr. Becker, well, it's what could be 1/4. Well, no, it's not, because we had the square root of 13, I believe, underneath the radical, so it's not going to come out nice. This is another example that if you took if you found delta, the discriminant, that would be what? B squared is 9 minus 4ac, so that would be 9 minus 8, which is 1, when 1's a perfect square. And look, see, we got two rational roots, two solutions, negative 1 and 2. And here, this is the second example I did, and you can see that the solutions, or the graph, does intersect the x-axis at positive 1 and negative 1/2. You can't tell that for sure just by looking at it, but since we factored it, we know. Okay. All right, so that's the deal between these two. I just wanted to hammer home the difference between real and rational. Okay. All right, one more page, and I still have this up here, and we are going to work this example together, and that'll be it. So we are considering this equation, kx squared plus k plus 3x equal to 1. Find the discriminant delta and draw its sign diagram. That might be something new to you, so we have to do that. Hence, find the value of k for which the equation has all of these things. Now, you understand k is a constant, x is our variable. So k being a constant can be any rational number. Okay, so first of all, we're going to solve that or set the equation equal to 0. Otherwise, finding the discriminant doesn't make sense, I suppose. I guess it could if you could look ahead, but anyway, this makes it nice and neat, and we move the 1 over, and here we go. So let's see. Let's just make sure we understand what A is and what B is and what C is. Here, A is K, B is K plus 3, the coefficient of the x term, and C is negative 1. So delta is going to equal b squared, so that's k plus 3 squared minus 4 times a, which is k, times negative 1. Okay, so let's see, that's going to equal, simplifying that, that's going to be k squared plus, 6k plus 9 plus 4k. Now again, this is just the discriminant. We're not factoring this quadratic. We're finding the discriminant. We're finding delta. Okay, and this simplifies into kx squared plus 10x plus 9 equals, yeah, that's that. We don't want to do the equals yet. So now what? Well, remember, with the discriminant, what we're concerned with is when the discriminant is positive, when it's negative, and when it is equal to 0. So I'm going to set the discriminant equal to 0. Oh, oops, this isn't an x, this is a k, sorry. Plus 10k plus 9 equal to 0. And let's see, so I can factor that pretty easily. K plus 9, k plus 1. Oops, 1 equal to 0, and I get k equal to -9 and k equal to -1. Now that makes the discriminant 0, and because of that, those are our, we can call those critical points, okay? Because that's when the discriminant is equal to 0, and that's what we are going to determine, or what's going to make our sign diagram. Okay, and our sign diagram shows us the sign of the discriminant for these intervals on the number line. For example, I'm going to test out -10 right here, or right here actually, and see what delta is if k is -10. Well, I think I can do it in my head. -10 squared is 100. 10 times -10 is -100, so that cancels out, and I'm left with +9, which is a positive number. That means I can be assured everything less than -9 is going to give me a positive result. I can test here, choose any number between -9 and -1. I'll choose something simple, -2. Again, I'll go up here and do it in my head, and I don't care about the solution really, I just care if it's going to be positive or negative. So -2 squared is 4, okay? 10 times -2 is -20, so 4 minus 20 is -16, plus 9 is -7. This is going to be negative. Okay, any value of k I chose between -9 and -1 would result in a negative discriminant. To the right of -1, I'm going to make my life easy. I'm going to pick 0. So that would be 0 squared plus 10 times 0, all is 0, plus 9 is a positive result. So anything to the right of that would make the discriminant positive. So now I can use the sign diagram to answer these questions. So for part A, when would I have two distinct real roots? Well, that happens, remember, when delta is greater than 0. When it's positive, I will have two distinct real roots. Now, distinct, okay, I have to be careful here. I can only do greater than 0, because if I included equal, I might get a double root if it's equal to 0, or a repeated root. So I can't include the greater than. Okay. So when is delta greater than 0? When is it positive? Well, it's positive when k is less than -9, or k is greater than, oops, I don't want equal, I just want greater than, get rid of that, k is greater than -1. Okay, so there's our solution for that. Take a quick look at a graph. If we chose k equal to 1, we would end up with a, which is greater than -1, x squared plus 4x minus 1. You can see we have two roots. It intersects the x-axis twice. I chose k equal to -12, which is less than -9. Replacing that into our quadratic back on the example results in this, and you can see here it also intersects the x-axis in two distinct places. Okay, so back to our example. What about B? Two real roots. Okay, well, what's missing here? The distinct. Okay, they're not saying that they don't have to be distinct, but by eliminating distinct, we're going to include the possibility that we have a repeated root. So if we have a repeated root, that means we would have to have a perfect square. So we have to include the equal sign, less than or equals to. Okay. And then if we want to guarantee a repeated root for part C, then our discriminant must be equal to 0. Well, if it is equal to 0, we just found right here that the discriminant is equal to 0 when k equals -9 or k equals -1. Whoops, negative, not a good negative sign. -1. Okay? And again, let's just take a quick look at the graph of that. What did I choose? Well, obviously I chose k equal to -9, and that gives us a double root, one solution, a double root. It just touches the x-axis one time. And then I chose k equal to -1, graphed it, and again it touches the x-axis just one time. And you're like, well, Mr. Becker, how is that an example of B or C? Well, I still had two real roots. Now that's roots here. That's not solutions. I do have two solutions. I just don't, they're the same solution. Roots is different than solutions in this respect. Okay, they may or may not be distinct. Here, a repeated root is saying, okay, they're not distinct. It's the same root, but it's repeated. Okay, so that's why I chose -9 for both of those graphs. So when would I have no real roots? Well, I have no real roots when the discriminant is negative. And again, looking at the sign diagram here, the discriminant is negative when the value of k is between -9 and -1. So my solution there would be -9 less than k less than -1, and we can't include equal to, because if it's equal to, we're up here where we have a repeated root. Okay. Quick look at some examples there. So I just had to choose some values between -1 and -9 for k, and I chose -8 closer to -9, and you can see the green graph does not intersect the x-axis, indicating no solutions. And I selected -2, which is closer to -1. And you can see the red graph does not intersect the x-axis, again indicating no solutions. So that concludes our discussion on discriminants. We will see you next time. Thank you very much.